First of all, today we're going to talk about the range and the rank of a matrix, and we discussed over the 2 sessions on systems of linear equations. And these systems of linear equations, we have denoted them as AX is equal to B. Okay, where A, it was the coefficient matrix, B was the answer vector, and X was the unknown. And so we started with a system of linear equations, and we also noticed that whenever we solve a system, the system may have no solution. It could have one solution or an infinite number of solutions. After we did this, we did some supportive material which can help us to understand better the systems of linear equations. So we worked on the determinant of a matrix A and the A inverse. Okay, so we were talking about, we learned about these 2 concepts, and then we should be aware that these are valid only when the matrix A is a square matrix. Okay, so we are talking when A is n by n. If we have a coefficient matrix which is n by n, that means that we have n equations and n unknowns. Okay, and we have some options here. Whenever the determinant of matrix A was different from 0, this meant that the system had only one solution. But having one solution makes the system consistent. Okay. Then the other option was that the determinant would be equal to 0, and in this case we could have an infinite number of solutions. Okay, and this is still consistent. Or we could even have an infinite number. Sorry, no solution at all. Sorry about this. So we could have even no solution. This made the system inconsistent. But this much material, so this is one solution, infinite number of solutions, this is both consistent. Then we could have also the other third option. But this is only when we have a square matrix, but this is not always the case. Now, if we have more general cases, what we mean with general cases, we mean that when we have A, it is n by n. Okay? So when the number of equations and the number of unknowns, it is not equal. Now, if we have any matrix n by n, which is the coefficient matrix, we can define what is, let's say, so when we're trying to solve this, we try to obtain, or we try to get reduced row echelon form of matrix A. Okay, so from this, we move to this, we try to obtain this reduced row echelon form, and as we try to do this, we try to obtain a matrix which is sparse. We try to produce as much zeros as possible to simplify the way that the information is offered to us. And then, after we do this, we check for the number of leading ones, So we check for number of leading ones, so we know that we try to simplify it as much as possible, and then this number would give us the rank of A. Okay, so this is, I'm going to say, this is a new definition for today. So whenever we simplify a matrix as much as possible, we look for the number of leading ones, or this is equivalent to counting, this is also equal to the number of non-zero rows. Number of non-zero rows. Okay, and then, so let's give an example. Let's assume that we have a matrix which is denoted as shown here: 1, 2, 3, 2, 3, 5, 1, 0, 1, 1, 5, 4. So here we have a matrix A, and we want to simplify this one. And here we have a 3 by 4, 3 equations, 4 unknowns, and if we try to obtain the reduced row echelon form, we have a leading one here, and then the next equation we can use is row 2 star would be equal to row 2 minus 2 row 1, or row 3 star would be equal to row 3 minus 3 row 1. And then, if we follow these steps, we obtain the following. We have 1, 2, 1, 1, 0, minus 1, minus 2, 3. Then here we have 0, 5, minus, no, 0, yes, 5, minus 6. We get minus 1, 1 minus 4, we get minus 2, and then we get 4 minus 3, we get another 1. Okay, we can simplify this a little further, which would be, let's try to obtain, this is a leading one. In order to get here another leading one, we can make this minus, we can make this plus, plus, minus, using the operation, which is row 2 star, would be equal to minus 1 times row 2. So this is what we get. And then after this, we can...
Professor.
Yes. Yes.
Since row 2 and row 3 are equal except for the last term, can we say that the solution, the matrix has no solution?
No.
Because
not yet.
They are equal except... Okay.
You are right. I mean, they are. That's correct. Thanks for making this comment. We have to keep track of how the numbers are changing. And but this is, I think we cannot say that yet, but let's see what we get. And first of all, let's see that this is just the matrix A. It does not have the answer vector. But let's see what we could do next is the following. We can say that row 3 star would be equal to row 3 plus row 2. If we do this, then the last equation would be 0, 0, 0, minus 2. And the first row is 1, 2, 1, 1. Here we have 0, 1, 2, minus 3. So we have the leading ones, and it looks like we have cleared out. So all this region below the red line, this is simplified, or it's a sparse matrix. We have a lot of zeros. And these are the leading ones. Here, we can do one more operation, which could be the following. We can say that row 3 star can be written as row 3 divided by minus 2. So this would end up into being 1. So here we have just 1. So this is the other leading one. Now the question is, the number of leading ones, this is as much as we can get. So this means that the rank of matrix A, this is equal to 3. Okay? Now, is this the reduced row echelon form? What can you say about this? Is this the reduced row echelon form of matrix A?
We can reduce it even further.
No.
Yes. That's true. So this is not the complete reduced row echelon form, because we know that the leading ones, which are these numbers, we should use them such that to make a 0 here. So they should be alone. They should be alone in their own columns. This one, this is alone in its own column. These are all zeros. This is 0, but for this one, we should make also this 2 0. And this one here, this should produce also another 2 zeros in here. Then that would be the reduced row echelon form. But from here, we obtain the important information, which is let me use this part, which is on the rank of the matrix A.
Professor.
Yes.
How did you get the rank A is equal to 3?
The rank, okay, because I just erased this one. Here we have written number of the leading ones. I'm putting this back.
And that's the rank of A?
Yes.
Okay, thank you.
So it is the number of non-zero rows, because it's always easy to get a 1, right? So we can count, we wrote another definition which I erased it. It was also equal to the number of non-zero rows, okay? Thanks for your question. So here we can construct a theorem which is the following. So for any matrix A, which is defined as n by n, with this we mean that for any matrix A, which is a square matrix, the following are equivalent. The following are equivalent, and these equivalent statements are the following. So A inverse exists. Second statement, AX is equal to B. Has a unique solution for any B. The third statement is AX equal to 0 has only trivial solution. This would be the third statement. Then we have reduced row echelon form. 4 is reduced row echelon form of A. This is equal to the identity matrix I. The 5, we can say that the determinant of A is different from 0. Okay, and the rank of A is equal to what? Would be equal to n. So for a square matrix, if the inverse exists, that means that all the information, we have no redundant information, which means that we have, if the matrix is 4 by 4, that means that we have 4 linearly independent equations in 4 unknowns. Now, let's see an example here. Let's assume we have the following equation. x1 plus 2x2 plus x3, this is equal to 1. 2x1 plus 3x2, this is equal to 5. 3x1 plus 5x2 plus x3, this would be equal to 4. So here we have a system which this is denoted as AX is equal to B. What is A? What is the size of A?
3 by 3.
Thanks, that's 3 by 3. And now let's see, let's try to use what we learned today for this matrix. So let's try to construct first the augmented matrix. From here, the augmented matrix AB would be the following. We have 1, 2, 1, then we have 2, 3, 0, then we have 3, 5, 1. Then the answer vector would be 1, 5, 4. 1, 5, 4. And then we have a leading one here. We need to make zeros around here. And if we follow the steps, the first equation would be, I guess this would be predictable. So row 2 star would be equal to row 2 minus 2 row 1, right? Row 3 star would be equal to row 3 minus 3 row 1. So then the next we get 1, 2, 1, 1. Then here we have 0, 3 minus 4 minus 1, 0 minus 2, minus 2, 5 minus 2, 3. Then we have here 0, 5, minus 6, minus 1, 1, minus 2, 1 minus 3, minus 2, and then we get 4 minus 3, we get 1. Okay, so here, this is the, let's notice that this is matrix A. Okay, so this is the matrix A, But here, which is 3 by 3, this other one is the augmented matrix A. So this is A 3 by 3. Then we have some other matrix which is 3 by 4. Now here we can produce here a leading one by multiplying the second row by -1. Okay, so we can make this plus, plus, minus, and then after we do this, we can say that row 3 star would be equal to row 3 plus row 2. In this case, we can get the following. Can somebody help me? What should be the answer here? The second row is...
The three rows don't change at all.
The second row doesn't change.
Neither the first.
Oh, the first, yeah, that's true. You are right. 1, 1.
And then we get 0, 0, 0, and 1 minus 3 is minus 2.
Okay, so this is what we get for this system. Now, what can you say for the third equation that we can see in this form here?
The system doesn't have a solution since 0 is different.
Yes.
That's true. So here we have 0x1 plus 0x2 plus 0x3. This is equal to -2. So it's impossible. We know that the division by 0, it is not defined. So for this reason, we cannot find a solution here. So we can say here no solution for this system. No solution, okay? And if you have no solution here, let's have a look at this theorem. What could you deduce from this expression? So apparently, here we have a unique solution. So this option of having no solution, it is not in here. So probably determinant of A, so let's write here. This means that it has no solution. In our case, well, we got a case, we said no solution. Now I'm writing in red what we got here in this example. Then probably it looks like if we have no solution, the rank of A, it is not 3. What is the rank of A?
It's 2.
Okay, rank of A is equal to 2. Yes, so it looks like we are still, everything is being negated. Why? Because these statements, they were equivalent. The moment that one of these drops, the others also could change. So it looks like the rank, it could have been 3, but no, it's 2. It's 1 less than this n here. What else can we get here? It looks like, what was the reduced row echelon form? Is it I?
Yes, it is, because we have 2, 2, 1. We can eliminate them and make them 0.
But it's not I, because to get an identity.
No, it's not I. Yes, right.
Okay, so it looks like it's not equal to I.
Professor,
Yes.
I have a question. The rank, what does it represent exactly?
The rank, it represents the number of equations which provide new information to us. This is the rank, okay? Now, if we found out that the rank is equal to 2, this means that we think we have 3 equations, but in fact there are only 2, okay? So which means that one of them is revealing some information which can be described by the other 2 equations. So let's see, how can we understand this from here? Actually, let me think. You could, if you see here, the third equation, equation 3, is equal to equation 1 plus equation 2. Would you agree with this? No. Apparently, no, it's not true. 5, 1. No, apparently it's not true, this one.
Yes.
But still, this has no solution. But wait a second. No, this is. Let me think.
Equation 2 is equal to equation 3 minus equation 1, but since it has no solution, they aren't equal.
We should not expect something like this because we have no solution. But let's check at the matrix A itself. What is the determinant of matrix A? Let's have a look for a moment. we can expand to find the determinant along the third column, okay? Which means the determinant would be equal to plus minus plus. We have 1 times 2, 3, 3, 5, plus 0 times something, plus 1 again, times 1, 2, 2, 3. 1, 2, 2, 3. Then this would be equal to, we can
Zero.
okay? Yes. We can choose a blank. So red is bad. Okay. So here we have 10 minus 3, we get 1. And here we have 3 minus 1.
Minus 1.
This is equal to 0. So it looks like the terminal here, this is equal to 0. So it looks like we are negating everything of these statements. So we have no solution. And then we can also look for the following. AX is equal to 0. Can it have any solution other than the trivial solution? Okay, so let's have a look here for a moment. Which means that if we want to check, and by the way, A inverse most probably does not.
It doesn't exist because the determinant is 0.
Correct. This does not exist, but let's check. So I think these three equations, they were trivial. Probably we can erase these, okay, because you know it's a simple step that we try to follow. And then let's try to do the following. So we have here 1, 2, 1. Sorry, okay. Or let's do it like this. What I'm trying to do is 2, 3, 0, 3, 5, 1, and then I want to solve this equation. AX is equal to 0. Okay, I want to check this statement. If we have any other solution other than a trivial one. Now, if we do it like this, and if we follow all these steps that we follow, would we change?
I think we have infinite solutions for that.
Well, let's see. I'm not sure. We have to check. That's a good option. That's a good option of having an infinite number of solutions. But if we start, look at this one. Instead of B, we put the zeros because we are checking this equation. We are not checking this. Okay. Then, if we follow the steps, most probably we are going to get this expression here with the zeros on the side. Because these zeros, if we do operations between the zero of the second row with the zero of third row, since these relationships are linear, we're going to get these zeros, they will not change, right? So here, would you agree with this? So the reduced row echelon form of this equation, it would be the following: 1, 2, 1, 0, 1, 2, and here the last one is all zeros, and then here we have 1. Sorry, no, these are zeros. These are zeros. The third row is full of zeros, so we can throw it away. We can keep it out, and then we can simplify this a little further, which would be the following. We can say that row 1 star would be equal to row 1, then what? How can we simplify this better?
Minus 2 or 2.
Yes, that's correct. Minus 2 row 2, minus 2 row 2. So then we get the following. We get here 1, 0, 1 minus 4, minus 3. These zeros, they will always be there. 0, 1, 2. And then this is the final set of equations. And it looks like we have 2 leading ones and 1 free variable, which is x3. Okay? So if x3 is a free variable, we can have the following equation. We have x1 is equal to 3x3. Would you agree here?
Yes.
Yes.
Okay, thanks. And since x3 is a free variable, we can say that x3 is equal to s.
Yeah.
And this is also equal to 3s. x2 is equal to minus 2x3, okay, which would be equal to minus 2s, x2, and x3 would be equal to s again, okay? So then, what is the solution vector for AX is equal to 0. It looks like the solution vector X would be equal to x1, x2, and x3, and this would be equal to a constant value s, which is any number in the real number space. This is 3, minus 2, 1. We have an infinite number of solutions, and so this is, so it looks like AX is equal to 0 has only a trivial solution. No, has infinite solutions. Good, so we check this one, this theorem for this specific case. Now, is this clear? I guess yes.
Want a thought,
Yes.
you can leave.
Sorry? Okay, now I think this part we did this. If we erase this one, we just want to check if we do a small change into this system. Instead of this 4, let's write here a 6. Let's make this 4, let's make this 6. Okay? And here we're going to get the following 1, 2, 1, 2, 3, 0, 3, 5, 1, and here we get 1, 5, 6. Now we'll try to simplify this a little more as we did before. So I think when we have this case, so this is the A and this is the matrix AB. So it is a matrix, it is an augmented matrix. This is the augmented matrix. And if we try to simplify this one as much as possible, the final result that we are going to get is the following. We're going to have this here 1, 1, 2, 1, 1. So the first one is not changing. 0, 1, 2, minus 3. And these are all zeros. Okay? So what we observed, sorry, what was this? Let's erase this one because this was a special case. So now we just changed this number, the 4, we made it a 6, and we come to a different solution. The initial solution is here in blue. And now when we see here, we have, does the system has a solution? What do you think here? Let's check what is the number of leading ones. Number?
Yes, it has an infinite number of solutions.
That's true. That's correct. And here we observe that the number of leading ones is what?
It's 2.
And this is equal to the rank of A. Okay. And how many free variables?
We have one free variable.
Only one. Free variables is 1, which is x3. Okay. And now this is what we have, and then so we can say simply that x3 is equal to s. Then we can have the following. We can say that x1 plus 2x2 plus s, which is x3, this is equal to 1. This is the first equation. The second equation is x2 plus 2x3, which is plus 2s, this is equal to minus 3. Then we can simplify this a little further, so we can insert this x2 in this equation, and we get the following. We get x1 plus 2 times minus 3 minus 2s plus s, this is equal to 1. Then this is x1 is equal to, we have minus 4x, wait a second, minus 4s plus s minus 3s, this is 3s. Then we get minus 6 plus 7. x2 is equal to minus 2s minus 3, and x3, this is equal to s. So it is pretty obvious that the solution vector for this system, when we substitute the 4 with the 6, is the following. So we get here 7 minus 3, 0, plus s times 3 minus 2, 1. So we see that actually this case, or this example that we solved here, this does not carry too much information related to this, but we could check this theorem, especially for the first case, because this was completely negating a few of the statements. So here we notice also an important factor, which is the following. So in the first case, which is this solution around here, we ended up having no solution. We observed that, what is the rank of A? What was the rank of A?
Rank of A was 2.
It was 2. What is the rank of AB? It's 3, right? The rank of the matrix AB, it is 3, because we have another one here, right? So, if we're looking for AB, this is AB. По матриц treме 4, the number of leading ones është 3. So the rank of AB is we have 1, 2, 3. So, and here we have no solution. If we have, whenever the rank of AB is different from the rank of A, we can say that we have no solution. In order to have solutions, we might expect a second case where the rank of A is equal to 2, and the rank of the augmented matrix AB, this is also equal to 2. So we have a solution, or the system is consistent. Okay. So this is sorry for a second. So this is the we have a major conclusion here regarding the existence of the whether a system has solution or not. This was the rank. Okay. And now that we are dealing with the rank, we are mostly working with the rows. Okay. Actually, I'm thinking whether we should cover the range right away, and then we come back to the rank for a couple of examples. Probably this is good. Let's define the range of a matrix. So, for the range of matrix A, this is a definition or a construct which is based mostly on the columns of A. So, we don't look anymore at the rows, but at the columns. And this is something essential when you consider the bigger picture of linear algebra, because the combination of rows, they define a specific space, and the combinations of columns, they define a different space. So, let's define, let A be a matrix which is m by n, okay? And then range of A, then the range of A, this is written as RA, is a subset of Rn, it is a subset of Rn given by range of A, this is equal to AX such that X is any number in Rn. Now here we have a fundamental question, or something that you can intuitively approach and not memorize it, which is the following. Now the range of A, is it a combination of the rows or of the columns? We partially answered this question, but let's consider the following. It looks like the range of A is a subset of Rn. Which component of A has n components? Is it the number of rows or the number of columns?
Number of rows. Rows.
Let's check this one. 1 minus 1, 2, 4. 3 minus 2, 4, 5. Minus 1 plus 1, 2 minus 2. What is this matrix? This is 3 by 4, right? And what is the range of A? What is the range of A? So here we see m is equal to 3 and n is equal to 4. I'm making a correlation between this definition and this matrix here. So it looks like the range of A, it is a subset of Rn. So in this case, we can say the range of A is a subset of R3. So which one has a triplet? Which one of these has a triplet of numbers, or can be defined by a triplet of numbers? Is it the columns or the rows?
Columns.
Okay, so we are talking about column space. So it looks like the linear combination between the columns of A, they define for us the subset in R cubed. So similarly, it looks like we have to look at the columns, but everything becomes a little more clear if we provide an example, which would be the following. Let's assume we have a matrix A, which is 1, 2, minus 1, 3, 2, 1. And then let's assume we have a vector A, which is equal to alpha 1 and alpha 2. The question is that these are given. So we're given these two. The question is, find range of A. Okay, how do we do it? Apparently, by definition, we multiply the A with any vector x. Now, why is this vector here not defined at all? Because they can be any number. When you say that it's a subset of Rn, that means that the alpha 1 and alpha 2, they can go from minus infinity to plus infinity. So if we multiply them, let's do the multiplication. So the range of A, let me think for a moment, yes, okay. And by the way, what is the size of A?
3 by 2.
3 by 2.
3 by 2.
What is the size of alpha?
2 by 1.
What is A alpha?
3 by 1.
3 by 1.
That's correct. It's 3 by 1. So it is a vector. Okay, it's a vector which, if we think about this one, so the alpha actually is better if we write this one x. I apologize. Maybe this is x, x1 and x2. That looks better. We are used to x, x2. Find x. So here we have ax. It looks like we're going to have a vector. But how will the vector look like? Let's multiply these. We have 1, 2, minus 1, 3, 2, 1. We multiply these with x1 and x2. And this would be equal to, so we multiply the first row with the first column. So we get here x1 plus 2x2. Then we have here minus x1 plus 3x2 and 2x1 plus x2. Okay, so this is the answer, and these are just numbers. So this is a single number, and this expression, we know that when we add two matrices that are both 4 by 4, 4 by 7, right? So two matrices that are 4 by 7, we can always split them, and here we can rewrite this equation like this. This is equal to x1 minus x1, 2x1 plus 2x2, 3x2, and x2. And we can factor out x1, which is here we get x1 times 1 minus 1, 2, plus x2 times 2, 3, 1. So it looks like the range of A, in this case, it is a linear combination of all of the columns of A. Okay, so this is how we can define the range of A. This is the range of matrix. We can go over a couple of exercises. So I think this is clear.
Professor,
Yes.
can you repeat, please, what do you mean by range? Didn't get it.
Shall I repeat this whole thing?
No, when we say range of matrix A, what's the range?
Okay, the range of matrix A, so which we denoted as RA, this is defined as the linear combination. This is the linear combination of columns of A. Okay, so let's not forget, I think when we provide the solution for a system of equations, we often we override this one. We say x is equal to p plus s v plus t w. Now s and t is a real number, okay, which is that this is a number from minus infinity to plus infinity. So it's any number. So now here similarly, we can ask the following: so let's look at the same matrix, and let's look at this question. Is 3 to 3 an element of the range of A? What do you think? We can check. We can check the
Yes, if we replace the x1 and x2 with 1.
Okay. Yes. Why? For x1 equal to 1 and x2 equal to 1, this is in the range of A, because we can write this one as the first column plus the second column. You are right, so it is true. Then the other question is, what about this vector? 2, 3, 1. Is it in the range of A?
Yes, x2 equal 1 and x1 equals 0.
That's true. So this is also yes. So this is how we are trying. What about this one? Let me ask you this. 5, 5, 5, and 5. Is this in the range of A? What can you say about this? You know,
I don't think this is in this part.
I don't think either.
you don't think either, okay? These are good guesses, but let's see. I was aiming to get a no from you. And how can I get a no from you? We can produce a no when we try to make up questions by doing the following. Let's do this one. Let's substitute this x1, let's make this 1, and x2 equal to 2. What do we get? Can you answer this for me?
Yeah, that's 5, 5, 5. Okay, so we have it.
No, this is 4.
Oh, it's 4. Wow,
So now, yeah, we get here 5, 5, 4. What I did is the following. I made this 5, 5, but I changed just one number, okay? I make it 5, then this definitely is no, okay? So if you want to produce, I mean, it's not the intention of this one, but probably sometimes I might be asking something like tricky questions. I say that find for me a vector which is not in the range of A, okay? We can define it, which is the following. So, but let's think about this one for a moment. Okay. So we give it a no, okay, and the reason is that intuitively we could do the following as we did here. The answer here is going to be 5. Sorry, this was 4, right? This was 4. Then, in order to produce a vector which is not in the range, you just change one, okay? Just change one while keeping the other two the same. But now let me ask you this other question. Now I might use the red color, and I can ask you the following. I can update this one with. Let me update this one with vector 5, 5, 5. Okay, because actually, what happens if I put here 5, 5, 4? Does the range of this matrix A change? So let's call this one A1.
You need to declare another variable, I think, x3 into a detail.
Yes, yes. But my question is this: how would you compare the range of A and the range of A1? What can you say?
I think now we have a 3D space.
Yes.
But before we had the plane of solution, and I think now we can get the 5, 5, 5 solution.
Okay, just keep. So let's do the following. You said let's use x3. Then let's try to use x3 as follows. So we can say here, we can say x1 times 1 minus 1, 2, 1 minus 1, 2, plus x2 times, what was the other vector? 2, 3, 1, okay, 2, 3, 1, plus x3 times, what was the other vector? 5, 5, 5, 5, 4. Okay, so this is the range. What is this? This is the range of A1. This is equal to this. Okay, that's good. But one thing that we can add here is the following, is that this 5, 5, 4, it is this actually. Okay, so we can rewrite this one as x1 times 1 minus 1, 2, okay, plus x2 times 2, 3, 1, plus x3 times what? Times, let's put here this nice looking parenthesis. So this is this vector 5, 5, 4. This is 1 minus 1, 2, plus 2 times 2, 3, 1.
That means this vector is parallel to the plane before, so it's still a plane of solution.
So, let's have a look at this one. You are right. You are right. But now what we get here is that the range of A, we initially thought that the range of A is composed by the linear combination of these three vectors, right? You see this one in red, but it looks like the range of A1, it is in fact equal to the linear combination of how many vectors?
4 vectors.
Any other answer?
I think
We can also write the vectors.
What did you say?
3 vectors.
2 vectors.
2 vectors.
It looks like just 2.
That's just
Just 2 because this is, we can write this one, I think we can write this one as x1 times vector v plus x2 vector w plus x3 times vector v plus 2 times vector w. So we are having just two different directions, right? the direction of given by this column and this column. That's it. So it looks like the range of A1, they are equal. The range of A would be equal to the range of A1. Why is this the case? This is the case because this column that we added, this is in fact written by this other two, so we are not adding anything new actually, okay? So the range of A1 is equal to the range of A for reasons that we intuitively answered like twice so far. Is it clear?
Yes.
Okay, but let's assume for a moment that we don't have here 5, 5, 4, which was a linear combination of these two, but let's make this 4, let's make this one a 5. Now, what can we say? Or let me, okay, I can ask another question at this stage. At this stage, let me ask the following. Now, let's call this on matrix A2. We are considering now what would be the range of A2. The first question is this: is 1, 0, 0 in the range of A2? What can you say?
I think
Which
yes.
one was it?
You think yes? Okay, you can give opinions right now. A possible yes or a possible no could be valid answers. I mean,
I think that because now that I know that the 555 is not a vector parallel to the plane before, and now we have a 3D space, and since there are only three coordinates, it has to be part of the space.
that's correct. Yes. So we have, that's true. So now this 555 is linearly independent of these other two columns. So we can span the three-dimensional space with these three vectors. And this is one single point in the three-dimensional space. Okay, so we can say that, yes, this is a number in, it's a vector in the range of A2. Good. And also 0, 1, 0. This is yes. Okay. 1 minus 1, 0. This is also in the range of A2. Why? Because for the same reason, we have these vectors are subsets of R3, so we need a triplet for each of these vectors, and we do have three vectors which are linearly independent. Okay, why? Because if we had only two, we can define a plane. If you have three, we can define the whole three-dimensional space. Okay, so to all of these, we can say yes, yes, yes. Okay, that's good. But we know that, so it looks like the range of A, and I can say it's not equal to the range of A. Sorry, the range of A2 is not equal to the range of A. Is it clear what you try to say here?
Yes.
Okay. So, so the concept of range, it is an important concept because it can tell us, or it can lead us into predicting what can we describe with these given vectors. So we had a case where we had three vectors, but we still could define only a plane. We could not get out of this plane. Okay? But if we get a vector which is not described, which is itself, if we get a third vector which is not on this plane, that means that you get the extra dimension. So we can describe the whole three-dimensional space. So we try to explain with using a little bit of intuition why the concept of range could be a useful component or a useful parameter of a matrix. Now, assuming, do you have any questions regarding what we have on the board? Okay. Okay, thanks. Let's see a couple of examples. So we know now what is a rank, we know what is a range. We know that the rank is something that has to do mostly with doing some calculations with the rows, but the range is something that we deal with the columns. So one has to do with the row space, one has to do with the column space. Okay. Now, let's see for a moment. Wait.
Can we do like a small break?
Yeah, I was just going to ask.
Yeah, we're going to ask for a small break. Okay, let me think for a moment. Yeah. You know, what if we continue a little more and we let me see. Actually, we've been going for like 50 minutes, I suppose. Okay. You know, can we go a couple of more examples? Because the major content, the theoretical content of this course, we have covered it. We'll just cover a few examples. Is it fine if we provide a few more examples?
Professor,
Okay,
we have had 7 hours of lesson today, and unë s'po marrë veç asnjë gjë çfarë po thua.
Okay, I give up. Okay. Okay, we give a break.